All right, so I'm going to continue talking golden section search. And the idea is, we're using the golden ratio here, okay? All right, so if here's we start off with a lower and upper bound, and we find x1 and x2, and the idea here is that these locations are determined by the golden ratio. So x1 is basically around around 62% of the way from the lower to the upper, and then x2 is around 0.61 of the way from the upper bound to the lower bound. Okay. And the idea is that, inside here we've got some function. Okay. And we evaluate the function at x1 and x2. Okay. So we'll say we know a local min exists between the lower and upper. Okay, and then we evaluate f at x1 and x2. Okay, and then here we find f of x2 to be less than f of x1. Okay. And because if f of x2 is less than f of x1, we know the minimum cannot be between f of x1 and the upper bound, okay? Because we know that there's already another point between x1, because we know there's another point that's smaller than f of x1. Okay, right, and it's f of x2. So from this, we can just eliminate this side. This side of our our search area, okay? And then so I guess this is our first iteration. And so the second iteration this remains my lower bound. x1 becomes my new upper bound. Okay? And then the beauty of this with golden section search is that x2 becomes the new x1. Okay? Because if I take these ratios of where 62% and whatnot lie, okay, then this becomes x2. And this distance, this is now around 61, the golden ratio from the upper minus the lower for the second iteration. And so we don't have to recalculate this value. This value still exists, and we can reuse that. Okay. So we eliminate x1 to upper. X1 becomes the new upper bound, okay? And x2, the old x2, becomes the new x1, okay? And we can we do not need to recalculate x1 or f of x1, okay? We will just reuse the old values of x2 and f of x2, okay? And this is useful for us because sometimes these functions that we have to evaluate are very costly, okay? And so you can imagine if it costs you $1 each time we ask the computer to evaluate f of some x value, we don't want to have to recalculate f of x every single time. So by being able to reuse a value, this is helpful to us, okay? And then so the next iteration, I have to calculate a new x2, and I calculate this value here, f of x2, and maybe we find f of x2 is greater than f of x1, okay? So let me just Alright, so now that I'm here, okay, this x1 and this x2, maybe we find this is the case, and because of that, we can then eliminate this side of the picture, okay? And then we would repeat, okay? And we would have, kind of a, this would become, for your third iteration, this would become the lower, this would remain the upper bound. This becomes x2, and then you would draw kind of a new line, a new location here, and this will be the new x1, okay? And you would have to calculate that, right? And so you can, at every single place, you can recalculate a new value, and we would continue honing in on what this final value should be. Okay, so our window would just get smaller and smaller. Okay. Is that all right? Okay. I've included a link to a video from University of Colorado Boulder that goes over golden section search. It's about 9 minutes long. I think it's well worth your investment of time to watch that video. So please be sure to check that out. Okay, are there any questions on this? All right. It's already been coded up for us, okay? And so I'm using just kind of, you have some function f, a lower bound and an upper bound, and then it evaluates all this stuff. I don't know what's going on with my screen here, okay? Okay, so I'll post that. All right, let me, now I want to talk about coordinate descent and just in general, multivariate optimization and some strategies, okay? So even more basic than any of these univariate optimization methods we've covered is what's known as the grid search, okay? So the grid search is a very simple but inefficient to find a local min or max. Okay, and the truth is in your homework, when I'm having you graph these things, I'm sort of having you guys perform a grid search anyway. Okay, the idea is you have a grid of points and you evaluate the function at every location. Okay. Okay, and that's grid search. Okay, we do this when graphing a function. Okay, graphing a function is very computationally expensive. So we might do something like x is a sequence from say -3 to 3 by equals 0.001, okay? So then what would the length of x be? Length of x is something like 6,001 points, right? Okay, so, and then I might do f of x as we take x and we plug it into the function f, okay? And so basically f has to be evaluated (6,001) times. Now, if the function is simple, this isn't a big deal, okay? But this is basically what we do, right? And then we might do something like plot x comma f of x, or we would do like ggplot AES map x to x and y to f of x or something like that, okay? And then R will plot all of these things and then connect them all with a line to kind of show a smooth curve, okay? But this is basically what the computer's doing when you have it graph a function, okay? So again, if every time we had f evaluate a function, if that cost us $1, it costs us $6,000 to graph this function, okay? So it's quite costly to do this because we have to evaluate f at every single one of these locations, okay? This, the inefficiency of a grid search is, worsened or heightened in multivariate settings, okay? All right, so what if we have some function of two variables? Okay, f of x comma y. All right. So let's say we say x is the sequence from -3 to 3. Y is 0.001. And then y is a sequence from -3 to 3 by 0.001 as well. Okay. In this case, if I do a grid search, how many times am I going to call f? So I have to look at every, we have to evaluate f at basically every combination of x and y. Which is going to be 6001 squared around 36 million, okay? And again, if each time we evaluate f, it costs us $1, now this grid search has cost us $36 million, okay? And you know, that's an exaggeration, but you just have to imagine that evaluating the function itself might be a computationally expensive task. And so if you can get your results without having to evaluate it at every single time, that's going to greatly speed up your the efficiency of your algorithm, okay? And then what if we had a function of 3 dimensions, okay? A grid search would then have to be, you know, 6001 cubed, and that's on the order of what, 200 billion, okay? So, you know, not ideal, right? Not a good situation to be in. Okay, but yeah, basically when you graph the function, you're doing a grid search, and when you graph it, you can just visually locate and say, okay, that's the minimum. That's easy to do. Okay. So what we do is we're going to look at coordinate descent. Now there's several ways to do optimization for a multivariate function, but we're going to just look at coordinate descent, okay? And what coordinate descent does is it says, well, if you've got a multivariate problem, you know, that operates in high dimensions, you know, your search space is very large, okay? And what it does is it says, well, you know what, let's simplify this down to a univariate search, okay? So we simplify our multivariate functions into unidimensional functions by holding all but one variable constant. So you have f of x and y. This becomes maybe just f of x, where you hold y equal to some y0 value, okay? This is univariate function of x. Okay, and then what we do is we find the value of x that minimizes this function. Okay, so we'll say x1 minimizes f of x, y, okay. I guess you can say x1 is equal to argmin over x of this function, right? Right. And then, so now that we have this, okay, so x1 is the value that minimizes. Sorry, there should be a space between the argmin and the f. I'll improve my handwriting here. Argmin f, argmin of x, of this, okay? x1 is the value that minimizes okay? So now, and that's basically it, and then we repeat the process for the next variable, okay? That is, hold all other variables constant, okay? Using the values you just found, okay? So then we'll have f of xy turns into f of y, where we're going to set x equal to the x1 that we just found, okay? Okay, and then once you do that, you just keep iterating, okay? So you hold one variable constant, and then you minimize the function according to the one variable that is free, and then you find that value, okay? And then you lock in all the other variables, okay? And you allow one variable to vary freely. So so I'll illustrate this in R, and I have to warn you, I have intentionally written my code a little bit poorly and inefficiently, okay? And part of the reason is for educational reasons, so you can kind of see exactly what's happening. And then the other part is you know, you have to do coordinate descent for your homework. And so I didn't want to give away too much of the answer, okay, for your homework. So so anyway, this is the function that we want to minimize, okay? So I've got g of xy, and this is equal to x squared minus 2x minus 0.5 xy plus 2.5 y squared. Right, so this is that's the function that we want to minimize, okay? And in here, oops, I'm going to create a sequence of x and y. You know what, let me just, yeah, that's fine, okay. So we'll go ahead and do that. And then I'm going to, an outer applies this function g to every combination x and y. And so if I check my environment, x is a vector of length 71, y is a vector of length 71, but z is a matrix, a 71 by 71 matrix, and each of these values is the result of plugging in, these different x values here into G, right? And that's going to allow me to create my plot here, and I'm using Plotly, which allows me to kind of create these dynamic 3D plots, which are, kind of fun to look at, but they are computationally slow to compute, okay? So don't do this in your homework, all right? You can kind of play around with it, and you can say, all right, ooh, here's a nice little 3D paraboloid, okay? So this is exciting, right? I don't know, can you guys see this okay? All right, so that looks neat. And basically we want to find the minimum here, okay? And so we're going to employ coordinate descent here. All right, so I'm just going to start off at some arbitrary starting point here, -1, 1.5, and I'm going to add that dot to the surface here, okay? And again, it takes a while to render, but we're going to start here, okay? So this is obviously not the minimum value, okay? But what I'm going to do is I'm going to hold my value y constant here, okay? And so if I hold the value y is currently 1.5. I'm going to hold y constant at 1.5. What we're going to have is basically there's like a little line that traces here, okay? And so to kind of illustrate this, all right, and again, this is highly inefficient, but I'm going to create a function where I'm replacing all instances of y with the number 1.5, okay? Now obviously you don't want to do this for your code, okay? But this is just to illustrate what I'm doing, right? So here's the original function. I'm replacing each instance of y with the value 1.5. And so now we can see this is a function of just x, right? X squared minus 2x minus 0.5x times 1.5. So I guess minus 0.75x. So I guess they combine to negative 2.75x. And then, plus some constant over here, okay? And so I've got some function of x, and I'm going to go ahead and add that trace to the plot here. Okay. All right. And so so here's where I hold y constant to 1.5. That's this orange line, and you can kind of see it on the plot there. Is that okay? And so I've got a unidimensional function of x, this orange line that appears here, and I just want to minimize it, okay? So we know how to do unidimensional optimization. Now, it's easy. I could just do the calculus, right? Take the derivative of x squared minus 2.75x and say, okay, x is half of 2.75, so 1.375, okay? I could do that. But I'm going to just plug it into golden section search and see how that performs. And if I plug this function of x into golden section search, it also spits out 1.375. Okay, so let me just start off. So our initial point is xy equal to, I forget where I am, -1, 1.5. Okay, so we start, we hold y equal to y0, and so g of xy becomes x squared minus 2x minus 0.5x times 1.5 plus 2.5 times 1.5 squared, and so this becomes g of x given y equals to 1.5, and this is x squared minus 2.75x plus, what is that? 1.5 squared is something. 2.25 times 2, I don't know, times something, okay? All right, and then we minimize this, right? Minimum of x squared minus 2.75x is at x equal to 1.375. Because you can, right, so g prime is equal to 2x minus 2.75 equal to 0. X is equal to... Okay, so, oh dear, what happened here? All right, so I do this and it says x1, that's the value that's going to minimize it, 1.375. So I'm going to go ahead and I'll plot that, and that's going to correspond to basically the bottom of this orange parabola right here that we are seeing. Is that okay? So I will go ahead and I will plot that. Oops, sorry. I will add that marker. Oh wait, you know what? Let me change it to a different color so you can see it a little easier. Okay, so there it is. That's the bottom of that. The bottom of this orange parabola is right there. Okay, and now that we have this, we are going to hold this value of x constant and draw a trace there. Okay, so again, to do this, and I'm doing this intentionally bad. Okay, I'm going to just replace every x value with 1.375. Okay, and so now you can see that it's just a function of y. Okay, obviously when you do it, you don't want to be doing it manually like this, right? You'll want to think a little bit and do it dynamically inside your program. Okay, but anyway, we'll go ahead and we'll plot this. Okay, and this parabola plotted on our plot looks like this. Okay. All right, so when I hold x constant to 1.375, it runs right through that minimum point here. Whoops, whoa. Okay. Oh, I did something here. Okay, oh wait, good. And it looks like this, okay? So it's hard to see, but we want to find the minimum of the function right there, okay? So at the it looks like this would be the bottom of our bowl, but technically the bottom is somewhere over here, okay? Because it's not. I don't know how to explain this, but the bowl is a little bit at an angle relative to the x and y coordinates. Okay. All right. So anyway, this is the center of this is the parabola when you hold x to be constant. Okay. It's just a univariate function, and we want to minimize this. Right. So we find x is at x equal to 1.375, and then so g of xy, given that x is equal to 1.375, becomes 1.375 squared minus 2 times 1.375 minus 0.5 times 1.375 times y plus 2.5 y squared. Okay, so g of y basically becomes 2.5 y squared minus whatever this is, 1.375 times 0.5. What is that? 0.672 0.25, I don't know. 1.375 times 0.5. 0.6875. 6875, okay? 6875y, and then this will, and we want to minimize this. So g prime of y will become 5y minus 0.6875. Set that equal to 0, and so you get y is equal to 0.6875 divided by 5, 0.1375. Okay, so that's going to be the value that we use. Now, we can just have R do golden section search for us, and it searches, and it also comes to the conclusion that the minimum value is 0.1375. Okay, so if you had to do it by hand, you could. You just have to do a little bit of calculus, right? It's not hard taking the derivative of a quadratic equation, right? It's like the easiest derivative that you could find. One of the easiest. Okay. So anyway, I'll go ahead and I'll add that. We'll do this in yellow. All right, and so the minimum, if I plot this, is going to be right here. All right, so the minimum of that white parabola is right there in yellow. That's this this dot right here, looking at it from underneath. Okay. And then so we repeat the entire process. We hold y constant at 1.375. Okay. And I think you guys get the idea by now of how this is working. Okay. And again, don't actually do it this way. Because this is highly inefficient, but I'm just doing it for illustrative purposes. And we'll add this plot here. Okay, and so that's the line you get when y is held constant. So this is the trace there. All right, and then we can say, okay, well, what value of x minimizes there, and we get 1.034375, and then we can add another marker here, and plot that. Okay, and we get something very close, which means we're getting a lot closer to the actual center, right? As you progress further into the algorithm, the iterations, those distances get smaller and smaller. And so we started here. We said, what's the let's hold y constant, and we get this parabola, and then we find the minimum for that parabola right here, and then we hold x constant right there, and we say, what's the minimum of this parabola, this white parabola, and we find that the minimum of that white parabola right here at the yellow. Okay, and we say, what's the minimum of this, and it's just going to be this orange dot right here. Is that okay? All right, and so you have an exercise like this in the homework. When you do this in the homework, okay, what's likely to happen is you got these these contour plots, and probably what you're going to see is you start off at some location, and because you're holding each coordinate constant, you're going to kind of get this stair-step pattern like this. Okay. something like this. Okay, so this is probably what you're going to see in your homework. Okay, it should look something like that. And you know, you just have to mess around with it a little bit. Okay. I think an issue that students frequently run into is that on if you use ggplot, the contour is a plot in 3 dimensions, right? You've got an x, a y, and a height, a z. Okay, and then you want to add segments to this plot, but you have to think you're now plotting in 3D. Even though it's looking directly from above, so it looks like it's in 2 dimensions, you're actually, the plot exists in 3 dimensions. And so your segments have a starting XYZ and an end point XYZ as well. Okay, so that's just something to keep in mind. I guess because you're plotting from straight down, like technically you could probably leave Z as a constant and it'll probably work fine. But just to say that your segments do exist in 3 dimensions here. Okay. Is that all right? Are there any questions here? So that is coordinate descent, and I'll post this code up if you guys want to play around with Plotly and stuff, and we'll call it a day there, and we'll see you guys on Friday.